In this video, I'd like to do two things. The first thing I'd like to do is to recall what a sampling distribution is, and the second thing is to look at what happens to the shape of our sampling distribution for mean when the sample size increases. So I'm in StatCrunch, and I'm going to go to the applets, similar to what we did in the last module, go down to sample distributions, and I want to look at a right-skewed population. And what I want to do is to calculate the statistic. I want to look at the mean. So here we have the population, which is right skewed. I always remember that it's skinny on the right. So skewed SK is the same as skinny. If it's right skewed, it's skinny on the right. It has a population mean of 14.0351. It has a median, a standard deviation associated with the population. And what I want to do is to take samples of 2. So I'm going to take samples of 2, and I'm going to look at the sample means. So remember, when I hit one time, it's going to take 2 samples. It finds the mean of those samples and plots them here. And we saw in the last module that this is going to create what is known as a sampling distribution of the sample mean. So we can do it again. And as we continue, it's going to continually make, let me click on 5 times, the sampling distribution for the mean. So what I'm going to do now is click on 1,000 times, and it doesn't show us that middle part. It just goes right to creating the distribution. So what I'm looking at is the distribution of means for every single sample that was just taken over that 1,000 times. So it looks like the mean that occurred the most was right here, less than 10, right? What we saw from our sampling distributions module was that the mean of the sample means will target the population mean. And we can kind of see that. The mean of our sample means, if I were to take all the means and find the mean of all those, I would get 14.0791, and the population mean is about 14.0351. So it's very, very close. We also saw that the median, right? We saw that was a biased estimator. That's not going to target, so the median is not going to look like the median there. And same thing with the standard deviation. So I'm going to do that another 1,000 times and another 1,000 times. This is, again, we've already kind of succeeded in our first objective, and that is to recall what a sampling distribution is. This is a sampling distribution. It is the distribution of the sample means. What we want to do now is to think about what happens to the shape when our sample size increases. So notice what I have here is I'm taking a sample size of 2. And if you look at the distribution, if you look at the shape of the sampling distribution, it is also skewed right. Our population was skewed right, and so is the sampling distribution for the sample mean. That's not a coincidence. So let's do another 1,000 times, and you'll notice that as you continually do that, it is still skewed right. So what happens if we increase our sample size? So let's reset this, but instead of doing sample size of 2, what if we increase it to, let's say, 5? Well, I'm going to go ahead and click on 1,000 times and do multiple samples here. If you've noticed, by clicking 1,000 times, I have now taken 37,000 samples. 37,000 samples, and this is the distribution of the sample means. It's not as skewed right as it was. It still looks like it's definitely a little bit more bell-shaped, but it's definitely still skewed a little bit here to the right, skinnier on the right than it is to the left. So when I increased my sample size from 2 to 5, it actually made it a little bit more bell-shaped. So I wonder what would happen if I increased it to, let's say, 10, a sample size of 10. Well, if what happened between 2 and 5 is any indication what will happen between 5 and 10, is that I'm going to guess that this is going to be even more bell-shaped. So let's go ahead and click that. It looks like it. It looks like it's not only becoming more bell-shaped, but it's also becoming what we would call maybe a little skinnier, right? The values are getting closer to the mean. So let me try one more time, but not a sample size of 10. we're going to take sample size of 100. And I'm going to do this 1,000 times. Well, would you look at that? Look how skinny, look how tight this is into the mean. This is a very tall bell shape, and it's also very skinny. This is leading us into the definition of the central limit theorem. The central limit theorem, as we'll see on the next page in this definition, is that the sampling distribution, as our sample size increases, our sampling distribution will become even more bell-shaped and even skinnier. Now, we're not going to have the exact definition use the word skinnier or more bell-shaped. We're going to have a nice, precise definition. But if you want to think about what the the central limit theorem is telling us and how we can interpret it and use it, is that when our sample size increases, the sampling distribution for the mean is going to resemble a bell-shaped curve more and more as our sample size increases, and it looks like the standard deviation is smaller, right? It's skinnier. The standard deviation is getting smaller and smaller and smaller, and that is also not a coincidence. So what we're going to do now on the next module page is get the definition of the central limit theorem and move on to how we're actually going to use it and what the central limit theorem can be used for.